All right, our recording is going. So now we're going to move on to a new topic area. So we've been talking over CT. And in some sense, if you've done the imaging class, we do kind of cover some of the CT ideas, not in as much detail or things of that sort, but we do cover the ideas of CT imaging. This is the first, what I would call truly, truly new ideas out there. Now, if you didn't take the imaging course, then it's all been new stuff, but a lot of people take that course and then this. So what we're going to do here is this is going to be dealing with nuclear particular imaging, which cuts down into two groups or two general types of imaging. There's actually more that's made of, but generally this is your SPECT type imaging and PET. Now, SPECT and PET are both 3D imaging techniques. So there is actually a 2D imaging technique that's out there called planar scintigraphy. And if you take, just like going from an X-ray image to a CT scan, it's kind of like a 2D image. You take a bunch of 2D images from different angles and you can make a 3D CT. So too, you can take a bunch of planar scintigraphy images and make a SPECT image. So, but generally, you don't see too many cases where planar scintigraphy is the whole goal. You know, I suppose there could be some, but that's usually the goal is to get to a SPECT image, a 3D image of it. So that's kind of where we're going to make the assumption on them. Anybody know the difference between nuclear images and like CT images and things we've been dealing with?
Where the radiation's coming from?
It's entirely the thing. Is it inside you or is it coming from an outside source and passing through? And then specifically what type of radiation you're dealing with is going to depend on, which imaging modality we're going to call it, right? So SPECT, single photon emission CT. So it's identifying it as a CT and it's just, one photon at a time. So it's going to be a nuclear decay situation where the output is going to be a gamma ray. And then we will also be dealing with PET scans. I don't know if we'll get all the way through to PET today, but PET is going to be, again, another nuclear decay, which is going to be positron emission tomography. And this will require new software. So I like to end really with, we've got 3 or 4 classes for this particular section. SPECT, honestly, nothing new there, other than where it's coming from. So we're going to kind of concentrate more on that and some of the overview ideas. But other than where it's coming from, you could actually use everything we've done before. You could use for SPECT, and you're done, right? Essentially, you get a bunch of images. You could, take those images that you get, put them into, your from different angles, put them into your classic sinogram, and generate the SPECT CT image. Exactly how you did everything else. PET, it won't work. You can't do that with PET. You'll get crud, and we'll show you why, right? But the real brief thing is there's just the signal rate is too low, and you get gobbled up by noise. So you really just cannot. You can't do this binning and spreading and everything else. As a matter of fact, we won't even be able to use like least squares techniques or everything else. We're going to have to use a technique that's going to have to take into account the probabilistic nature of these type of decays every bit as much as the transmission regimes it goes through. So we will very heavily be dealing with what's called expectation maximization type methods. So just as a curiosity, has anybody seen expectation maximization before as a method? It'll be kind of new for everybody. What we'll probably do is hopefully we'll get to this next time. And we'll just do some small things just to get you used to them, and then we'll build up to how does it work inside of an actual tomography situation. And it'll surprise you how good of a job it will do, even with these ridiculously low data rates that are out there and horrible noise situations. It'll still generate a clear image when there's just nothing good coming out of least squares. But it is a very, very helpful modality that's coming in. All right. So that's kind of my quick overview of where we're going and how it relates to the rest of this. So I want to talk a little bit about some of the stuff. This is actually an image from the book, but I can't really get you a better image, so I'm just going to steal theirs. So why would we want to do some of these internal generated radiation, right? I mean, think about it for a second. I've got to basically put a radioactive isotope inside your body, right? And because of that, I got to think twice, before I want to do it. I should do that with any type of radiation I'm applying to your body, but it just seems even more so when I'm actually injecting you with a radioactive pharmaceutical or what's called a radiotracer. But the difference is that you can tell function, not just form. So when we were doing the transmission types, right? I have an external source and an external receiver, and it passes through. Right? I can see the form, what your body is, by telling materials that the photons interact with. But, right, I have no idea how they're working. Right? I just know what their shape is physically. So I can give you a good physical model. When you're dealing with this type of nuclear medicine, what I'm actually imaging here is no longer what is the shape of the thing you're dealing with. It is what is the function of the thing you are dealing with. Because what we're going to do is we'll tie these radio tracers to a biopharmaceutical. Right? Classic example is actually the next image here that's on. This is, say for instance, if I'm looking for some particular biofunction, maybe I'm looking for a tumor or whatever else, right? I'm going to take a pharmaceutical, right? Something that's going to be reacted upon by your body, and I'm going to pick something like, say for instance, glucose, right? And I will tag a radioactive isotope to it, and I can watch where sugar goes in your body. Therefore, I will tell, and I can take this over time, so I can even see the rates of uptake and how it changes inside in response to different, demands put upon your body. So I could do it with glucose to take a look at metabolism. I could also tag it to oxygen that's going to be within your blood, right? And again, be able to tell metabolizing areas. But there's all kinds of different, think of the wealth of pharmaceuticals that are outside there, right? If I wanted to look for a particular disease, I could get a pharmaceutical that is specifically designed to latch on to certain protein binding sites and just pick a protein binding site that's associated with a disease. At which point I can then find out wherever that disease has been located inside your body or any other type of activity that I would like to do. I can make things that are rapidly dissolved into certain types of tissue. That's actually what the previous one was. So this one is myocardial perfusion. So the perfusion in here is how this particular substance is being uptaken by cardiac muscles. So usually you'll pick something like oxygen or some other type of a gas that's going to react similarly to that. And I want to find out, for instance, here on your heart, where exactly is is there a lack of blood transfer to some area on your heart? And you can see, for instance, the really high uptake on one side of the heart there, right? You can see those kind of bright regions. That's your left ventricle. So the left ventricle is the biggest muscle part of your heart, because that's the one that's pushing everything out throughout the whole body. So being the biggest muscle, portion of the heart, it's going to uptake things very, very fast. And you can see it's pretty even across that muscle. Yippee-ki-yay, that's great. That's telling you that the perfusion, the spread of the oxygen throughout that muscle, it's getting equally done. If you had a heart condition, you would have some portion, like some blockage on the outside of your heart. A portion of that muscle would not be getting the oxygen transfer, and you would see an area where it is not as brightly coated with the radiation on it. So you could see, oh, there's a portion of the heart that it's just not actually getting blood flow. All right, so that becomes kind of a nice quick way to check and see, how is this working? And you can see they do it in 3D. So on the top, they've kind of done axial cuts. So you can kind of see the round area, right? That's, aorta getting pumped out, right? And then moving down, and you can see on the other ones, they've done like sagittal cuts, so you can see the cross section inside, so you can see the U shape of the muscle that's squeezing it. So just like a CT, we can slice it up different ways because it's a true 3D image. But this would be an example of something that's being done with SPECT, right? So it's basically, it's going to tell you, take pictures of where photons are coming from a radioactive source. This is not a typical thing you would do with a PET setup, right? So this one, we want photons as our decay methodology. Makes sense what we're doing with SPECT? So now you can, whenever you're thinking of nuclear medicine, whatever type of it is, whether you're doing SPECT or you're doing PET, you want to think of, I'm looking for a function. Right? If I'm looking for cancer, I'm looking for super high metabolism. If I'm looking, for instance, they'll do this to try to diagnose Alzheimer's, because cells affected by Alzheimer's have a slightly lower metabolism than other brain cells. Since it's a slightly lower metabolism, you can watch the uptake of sugars inside the brain, and you'll see there are certain regions that are going to be slower uptake, and you could actually image the spread of Alzheimer's across somebody's brain if you know that's what you're looking for. You pick the appropriate pharmaceuticals and the radio tracers for what you're doing. Make sense? Awesome. So that's the basic idea, but keep those two portions in mind, right? We need, we need to have some type of a pharmaceutical that's going to take it to where it needs to go, and then we need a radioisotope that's going to decay in the way that we want, in the time frame that we're going to have to be dealing with. So that's going to be another important issue, right? You've got to get a certain number of photons coming out in a certain time period. So these are PET images here. PET images are usually nowhere near, you can see they're not as particularly bright, because what usually you get on these, some of this stuff is going to go everywhere, which is why you get low levels, but you'll get particularly high concentrations, and you're trying to target certain areas where whatever the condition you're looking for is, whether it's cancer or some other type of activity going on within the body. You will also get a large concentration of this in the bladder, right? Because that's how all of this stuff eventually leaves the system, is the body processes it, it gets accumulated within the bladder, and then somebody, pees it out. So essentially, there can be like bladder cancers and stuff of that sort that you're looking for. So you would have to watch the rate at which it's filling if you're suspecting something along those lines. But it'll all eventually end up in the bladder. Yeah.
Are there many of these radio tracers, or the little radioactive things you put in them, that are so well concentrated that you need to couple it with regular CT to see where it is in the body, or did most of them give you?
You almost always are going to couple this with regular CT.
Okay, cool.
You can notice here, you'll never get such a heavy doses, and you don't want too much, because think about it, right? You're basically emitting a positron. And that positron has to hit an electron and emit, the two X-rays that come off from this, basically, right? Particularly high energy ones, but still, a result of that positron electron reaction. You don't want too much of that inside the body. It's, in general, it's, you will still get an image from it, which, that's a good feature, and you count as part of the imaging dose, but still not the most desirable thing to have going on. So we figure, hey, we want to keep this down to a minimum, and we're just trying to find where it is. So if you imagine, this type of thing is particularly useful if I'm trying to see if cancer has metastasized. And if so, where has it metastasized to? Since it'll be uptaken by those cancer cells, and I could even pick, like let's say for instance, there's some known particular hormones that are associated with breast cancer. And so, if you're looking, breast cancer will often move to the bones. Right? So that's they'll get out into the bloodstream, they'll move to some of the lymphocytes, but their eventual goal is to get into the bones, and you get these secondary bone cancers. So how do you know where the breast cancer is so you can try to target your treatments to take care of it? Getting something that's going to particularly tag, that one allows you to find its locations and therefore, locate them. And, in general, so you're just trying to find locators from it. You just need enough from these then to overlay to the human body. So you're going to have a CT scan where the person is in the exact same position. Right? That's why it's often nice for a lot of these to have kind of a dual one, so you don't have to move the patient. You can take one image and then do the other. Since you don't often get those combinations in these single machines, they'll usually just take it one room to the next and just wheel the person on a cart and move them. But that overlay is pretty much always gonna be used. They put this on here because otherwise you wouldn't see what the raw image looks like. And there is a sense where looking on this, you can kind of quickly identify where the particular targets are for this. Yeah. Any other questions? Awesome. All right, so we have to go back a little bit nuclear stuff and just kind of a refresher, but B, covering some of the particular interests. Those two different types we're going to do require different decays. So stole both of these from the book too, just it helps to kind of understand what's going on with them. So the one on the left, what we've listed, this is protons plus neutrons in the line, right? They're going to horribly reuse the letter A later on for a completely different reason within the book. So just get used to it. Right, so this, whenever you get an atom that forms, right, you get a bunch of protons and a bunch of neutrons, a bunch of electrons, and they all combine together. If I take all the protons and neutrons and electrons mass, and I compare it to the mass of the atom, how should they compare?
Well, it should or actual, or
What?
well, there's going to be a little bit of binding energy. So the energy of the atoms is going to be a little longer. Or sorry, the mass of the atoms is going to be a little longer.
Yes, so the mass is smaller, right? This is sometimes that kind of lost mass. This used to bug people quite a bit early on until they discovered what it's being used for. This is the binding energy. The total energy, right, has to be constant. You can't, make it. You can shift it, according to Einstein, between mass and energy, right? To bind everything together, you need some of that energy. So some of that mass has to get converted into a binding energy. As the things get bigger, you get more and more. It's a straight increase. So what they do is they'll take it and they'll take the total amount of binding energy, which is this quote unquote lost mass, converted into energy, and they'll divide by how many nucleons are having to be bound together by this energy. So that's what they're plotting here. Right? So you'll see there actually is a peak right here around 50 or so. You kind of hit that peak. That's the sum of the two. And remember, you have a little, once you're past the very low level stuff, you're going to have a little bit more of the neutrons than you will have with protons. All right, so that's just kind of to separate these up. This is the the stable nucleotides. You'll see it goes all the way out here to uranium-235 that's on. Anybody got an idea what's going on with the length of this particular chart here? That plutonium-208 is kind of in that important zone. The highest stable nucleus has right around 82 protons, right? And 126 neutrons, so a total of 208. There is nothing above 208 that's stable. Right? It doesn't mean that being at 208, there's other isotopes that are not stable. Right? Plutonium obviously decays and stuff. But the highest stable nucleus is at 208. Right? So everything above that, unstable. So when they're on here, they're deliberately trying to just plot up no nuclei, whether they're stable or unstable. There are ones that actually go beyond that, the 235, but they're usually so short-lived, it's kind of not worth it, and it's not in our sort of interest. But if you look, interestingly, the binding energy starts dropping off actually as you get heavier. So even though the total binding energy out there is higher, the binding energy per particular nucleon is getting smaller. Now, in general, things are going to rearrange to try to get to more stable values. And that's what's happening with these nuclear decays, is they're going to try to rearrange to get the stable values along this curve. So that's the whole idea. Any of the isotopes off are going to move towards it. So this is kind of like where all of our stuff is lying along when we're picking our isotopes. Okay, I stole this from my earlier one. So, but I thought this was kind of an important one and I didn't like the book's descriptions of any of that. I thought this is a better picture than what they give you. Because what you'll notice on here, first off, those are the types. In truth, these are technically considered the same, right? These are technically both a B plus, but you could get the net thing by either emitting the positron or having an electron capture go on. The net effect is the same, or pretty darn similar, right? This is going to go off and it will collide with an electron at some point, then you will get an X-ray. Now, in truth, that shouldn't say X-ray, so that's actually bad. This is actually a gamma ray. This one technically goes off and then causes an X-ray. Just out of curiosity, anybody know the difference, the actual difference between X-ray and gamma ray?
The book said that gamma rays come from nucleus, X-rays don't.
Yeah, that's the. So technically, if this was coming right from a reaction on here, that should be gamma, because it is a source. Now, I don't know if they mentioned this, or not. It's been a while since I read the book, but in general, the reason why most people consider gamma rays as higher energy is because most of the things coming from the nucleus have a lot more energy than X-rays, which come from the electron cloud interactions. And since, in general, X-rays have less energy because they're having a lower energy event, usually not. Now, the highest one you'll get typically from a usual electron cloud interaction will be a positron slamming into an electron, which will give you the 511. Just remember that's the rest mass of an electron. That's usually about as big as it gets, whereas you can get quite a bit larger gamma rays coming out from the source. Anyway, so alpha decay, right? Beta decay, which is an electron, right? We don't want either of these. Right? And the reason why we don't want either of these is that, this might end up eventually creating something that we want, but in the meantime, you've generated other radiation, particularly like alpha particles inside your body, really damaging. There are some times we actually would have some of these inside your body, but that's usually if we're trying to particularly put something, they don't go very far at all. These are very low energy, but when they hit, they cause a lot of damage. So low energy means doesn't travel far. So can you think of a reason we might want a not travel far radiation source that kills anything in the vicinity?
Skin cancer?
Yeah, cancers and things like that. What if I put a radioactive seed and I place it inside a tumor? These will only travel so far, and whatever they hit, anything in that near vicinity is going to get killed, right? So then it's just a question of how do you ideally place those little seeds to be able to basically, annihilate stuff. That's brachytherapy, yeah.
Yeah, what do you mean by like a seed?
A seed is a little tiny radioactive isotope pellet that's placed in the area. So it's done for several types of cancer. One of them is prostate cancer, for instance. You'll get these fairly bad. And they'll place little tiny radioactive, they call them seeds because they're really small. And they just place them in a particular pattern so that the cancer itself just gets killed by these radioactive sources. But they can't travel far enough to go out. Right? Now this is an interesting segment. It has nothing to do with the book. It's not really on our class because we're not doing medical imaging, but you'll see in a second why I mentioned it. There is a neat correlation to Baylor for this technique, right? So the mathematics for how do you place the seeds was actually done by Robert Marks. This is one of his claims to fame. So he's the guy who solved that mathematical problem of how do you optimally place those to take them out. So it's kind of a cool Bob story. There's a reason why Bob is fairly famous. He's done a lot of cool stuff like that. So, but that's a place where you would use these, but this ain't one of them. We're doing imaging. You're putting it in something we're trying to save. We don't want that to happen. Right here, excited nuclear state to not excited nuclear state emits gamma, right? That is what you want for SPECT. So right here, this gamma decay, that is SPECT. Anything that has a gamma decay, candidate for it. We don't want some other decay leading to a gamma decay because that some other decay is extra radiation to you that cannot be used for imaging. So we generally don't like that. We really want gamma decay. Right? The positron emission, this is PET. Right? Like I said, with this, this is actually very, very rare. You have to have very high energy electrons to do that. We just won't put you in an electron beam. It's coming out of a cyclotron and work pretty good. So these are the two ones we're going to care about: SPECT, PET.
You mentioned that oftentimes when a positron leaves, it'll just find an electron and annihilate.
It always will,
Okay, so
because it's antimatter.
right.
It'll travel up to about 1 millimeter or so
Okay.
on that range. So when you're doing PET, you're gonna actually have an error associated with it. Because it's gonna travel in a random distance and boop. And so when you get the trace them back, you'll get essentially two photons that will go off in completely opposite directions. They're guaranteed to be 180 degrees apart. You don't know what their orientation is, but they have to be 180. Anybody got an idea why? Yeah. Right? Because if it wasn't, if they were a little bit off, there'd be a net momentum that had to come into it. There's not, so they have to be perfectly 180 apart during that collision. Right? So it'll travel for a short distance, millimeter or so, wham, you'll get these two, and then we'll detect them on a big ring that's around there. We'll get into this more next time, right? But we'll have a big ring around it, and we'll measure time for when does it hit on each one, and then we can trace them back. So we'll get the time differential between them. By knowing the two, we draw a straight line between them, right? And then the time differential will tell where it is. If the time differential is 0, it was right in the middle of that line, right? If it hits this one earlier than this one, it's that much time-wise on the other side of it. So you can actually get your position off of it, and that's the trick to looking where it came from. But then you realize that it could be a millimeter or so different from there, because it had to kind of go boop, 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 boop until it eventually hits something. How far it'll travel will be a function of the amount of kinetic energy it pops out with. More kinetic energy, further travel. So anyway, the ones that are going to do, we want these B+, and look how many there are. See all the orange ones on the bottom here? Those are all your B+, because they're in essence going to swap a proton for a neutron, so they'll move diagonally this way. And there are a lot of them. We do not want these blue, that's the electrons. And then for our, we want our gamma decays, single nuke. There are a couple that are on here that are high energy. They might not be plotting those isotopes. So there are some particular ones where there are decays where you start and end with the same thing. And since this one is trying to say changes, I don't think this graph actually shows the ones that go on. There's usually there's a decay that'll go from what's called a metastable state down to a stable. Usually what happens is there's like a decay like cesium-137 will turn to barium-137, giving off an electron. Right? These are fairly slow processes. So you can get a decent amount of barium-137 built up, and then the barium-137 is a metastable state. When it comes out of the reaction from cesium-137, it's got too much energy in the nucleus, and it'll undergo a gamma decay from barium-137M to barium-137. And then barium-137 will then have a decay that goes to something else, right? But essentially, you know, I don't think they're actually, as I'm thinking on this, they probably don't even try to plot the metastables on this, because then they'd have to split those pixels into two colors. But there are a bunch of them, and as long as the decay rate is slow enough, I can build up the metastables. I can generate them, build up those metastables, and then inject you with the resulting metastables, right? And I'll let you go from there. So, but that's generally, we want the metastables as the basic byproduct that we care about to get these ones for specs. Yeah.
So Luke talked a little bit about neutrino emissions. Are we gonna worry about those?
In general, do people worry about them? Yes. Are we going to worry about them? No.
Okay, great.
No. There's a ton of stuff that's out there, and I would encourage. So there are a lot of programs that are out there. If you really get into this type of stuff and you determine, hey, I really like this, I want to go into this. This is where there's what's called a medical physics degree, and you can take the output of what we're doing here and get a medical physics degree. You go on some extra courses and whatever, and it's a very in-demand field. Right? They pay a lot of money for it because at any hospital doing any of this type of imaging or treatment, they have to have somebody who can generate these particles and determine the doses and everything else to a high degree to do the planning, everything else. So they're very well paid and they're all over the place. You know, there's not gobs and gobs of them, but relatively speaking, it's a pretty good market. They tend to do quite well. So that is a potential direction. I have had some former students go on and go into medical physics because they just happen to like this route. But it's not our main thrust. And that's when you would hit into those. Awesome. Okay, so let's talk a little bit about radioactivity. So have you guys done radioactivity anywhere else? Did they cover it when you did physics? Okay. So, the basic unit most people use is the Curie, right? But the Becquerel is actually what the SI unit is, right? So the BQ, that's the SI system. The Curie is the older one that's on there. A lot of people still use the Curie because it's kind of the classic thing. And honestly, even though I understand the reason why, right, the definition of the Becquerel is much more logical. 1 decay per second, right? A DPS, decays per second. That's kind of a nice basic unit. It means something to you. The one argument I would make for the other one is it actually does two things for you. Number one, it preserves the history. Because like Adam Curie and some of those early people literally died to get us this information, learning how it works. And at some level, you deserve a tip of the hat for like literally killing yourself to advance human knowledge. So I like to include it there because I think it's a tribute to people who really went above and beyond. That's on there. And second off, she picked those numbers because it was based off rates that made sense for what, you know, she was trying to do to get easy measurement. Now figure she's early on in this process, right? Late 1800s, right? So do you think we need that much, or do we need more, or do we need less of radiation decays? Because what you're measuring here is decay. So, you know, compared to an early on thing, would we need more or less or the same? Why do we need more? You might be right, so I'm just asking the reason.
Be less, because we have more sensitive detectors and such.
You're saying you're asking us to step into.
I'm just saying, yeah, relative to her, what she had to deal with, do we need a higher decay rate or a lower decay rate? Yes.
Yeah. I thought you were saying putting myself in her shoes.
Oh yeah, no, she needs obviously more.
Yeah. Okay.
You know, so if you think about it, we're gonna actually deal with, and you would imagine that was like 100 years ago, we're probably a bit better. And that's actually true. Most of our things are on the order of about 1,000th of what she was using on. So we're kind of in the millicuries. So the reason I kind of like that unit also is, you know, if I just tell you a decay per second, you know instantly what that is. But is that good? Is that bad? You know, where is it in the grand scheme of things? Whereas when you're dealing with the Curies, you can go, I'm 100 years later. It does kind of make sense that over 100 years that I'd be 3 orders of magnitude better. That's a pretty easy to remember. So remember that you're somewhere in the millicurie range whenever you're doing medical imaging. You know, millicurie or a fraction. Millicurie is about the upper end. So somewhere between like 10 to the 4 and 10 to the third, you know, 1 over that, right? 10 to the minus 3, 10 to the minus 4. That's about the range you're at with how many decays you need per second to get an effective image for us. So there is kind of a niceness to that as well. All right, how do we actually find out? So we need a certain amount of intensity hitting our detectors to record it. This is how many actual decays we have. So that's what these numbers are quantifying. How many decays per second. This is how much energy in the photon that's being released. So we can see over here, if we take a look at different, you know, nuclides that are out there, right? We've got our protons. This gives you what your half-life is. This is the photon energy. So we could see, for instance, you know, this is a fairly typical one that's used. You can see here the 99M is going to go to 99. Right? It's just removes the M. So you can see the M's on a bunch of these. These are metastables that are, you know, those are already in them and away you go. And even the metastables, you can see they're still, you know, they're in the order of a few hours for them to be able to decay and go away. You know, you can see there are other ones. Do they have? I don't think they'll show the CJ one I talked about. All right, but anyway, these are the standard ones that are out there that are going to have those decay rates. You can see on a lot of the other ones, you've got day decay rates, but you get the energy. So let's say I was just dealing with the technetium, right? The photon that comes off it is 140 keV. So that 140 is what goes into the energy E, right? And A is however much of this is, right? 10 to the minus 3 pure A's or whatever. We always put it in the backgrounds though, because that's the SI units, so we want consistent units through it. But I do think the Curies are helpful in that they'll kind of give you a ballpark range of where there should be. Now, in particular, calculating that A, somebody could just tell you this is what it is, but if you had to actually calculate it, and the book mentions it, it's really not that fancy. All of you have dealt with the half-life equation before, right? I just combined this, right? It's minus because you're losing stuff. N is the number you've got. So the change in the number over time is lambda times however many N is. So it's proportional to that area, right? This is the disintegrations per second. So that's what A is. So that's just there to kind of put it in the term. When you consider your basic equation, it's worth noting because of this, I could just go through, since lambda N is A, if I just went through and multiplied both of these by lambda, right, then I would have d lambda N dt is equal to lambda times lambda N, which is dA dt is equal to lambda A. So just note, if the equation works for N, it works for A, because it's just a constant of proportionality. Lambda is a constant for whatever atom type you have. Therefore, it's if you've got N or A, that's where you end up with the same equation for either one. Again, you just multiply through by lambda, boom, there you go. This is a first order equation, it pops out. Whenever you see this first order equation, right, what jumps to your mind though? There's something should, as an engineer, something should always jump to your mind when you see this. What's that? Yeah, it's that whole, right? The whole reason why this is working on is exponentials are the fixed point in calculus. And because they're the fixed point in calculus, that's why Fourier transform works, right? So Fourier transform is even kind of showing up in a sense right in here because it's showing you that basic constants that are going, the mathematical formula of it, works even at this point. Right? So it is a really important idea that's coming through. This is just how do I get the lambda for it? They always give you the half-life. Right? So this is just the natural log of 2, right? And it would be minus that, but it had a minus sign, so, So this is the natural log of 2 divided by whatever the half-life is. That is your lambda. So when you're looking to calculate to get lambda, which is needed to be able to get A, if they don't just give it to you. Again, you use this same chart here. You've got your half-life, stick it in this equation, you've got lambda. So fairly straightforward. There are some homework and some other stuff to do, but it's really just, pull the numbers from this chart, stick it in there, and away you go. So should be fairly straightforward type of stuff. We feel good with these? So these ones are all the gamma emitters, at least the most common ones. There's also, for the positron, these are positron emitters that are kind of standard ones. Again, their half-life, how much energy they come out with. So kinetic energy plus the positron electron annihilation gives you the total energy that's going on in those. All right. When we look at rates, typically speaking, if you notice, most of those were half-lives in terms of hours. All right? Now, if your time period is a half-life, but it's on the order of what you're measuring, then you would expect the amount of the material to be changing, so the half-life is changing over your period. Right? If you're at a small fraction, right? It's the half-life is in terms of days and you're measuring over several seconds or something. You're at such a small fraction, you don't really expect N to be appreciably changing. It's too small compared to the half-life for it to really matter. If you notice, most of our ones, they're fairly long. I don't know if that kind of struck you when you look at these areas. These are in minutes typically for most of the positron emitters. But like, look at some of these, right? 120 days, right? I mean, even the 6 hours, right? Or, you know, you got almost 3 days, almost 2 hours, you know, 13 hours, right? Is somebody going to sit there for hours? Yeah, no way, right? How long can you reasonably expect a person to be there? Half an hour, or somewhere maximum. Usually we want to keep it 10 to 30 minutes. Part of the reason being, again, in addition to whatever's going on here, your body is metabolizing that, right? If I give you a bunch of sugar, how long does that last in your system? Yeah. So even if the radioactivity is still there, it ain't where it's supposed to be anymore. It's been metabolized and it's gone through your kidneys and it's now waiting for the person to remove them. So now all I'm doing is imaging their bladder if I leave it in there too long. So I sure don't want that to, I mean, that's like a waste. So, right? But these are way too long in terms of our imaging time periods. So what gives? Well, these are of their nature going to require you to have, you know, essentially your imaging in a small fraction. So now we've got to consider probabilistic, right? Decays themselves are random. And since they're random, we now have to be able to say, well, when I'm dealing with a very, you know, small bit of a larger time period, when a decay happens, you know, may move towards the mean, but what does it really look like? So that's what we're trying to talk about on these, because I have no choice when I'm dealing with SPECT. So this is really kind of a SPECT issue, right? Is it going to be a PET issue?
Based on the question, no? I don't know.
Not anywhere near as much, right? I mean, if you look at a lot, there's a few, like copper 64 is a little bit longer, but our worst case is in hours. So there will be a few where it is on there, but some of these are like 10 minutes, 2 minutes, right? If I'm doing with oxygen 15 and I'm trying to track your metabolism and things like that, you breathe that one in, right? So essentially in here, I don't have any problems on this one. It's already in the order, so I can consider a lot of these are going to be on the order of this. Again, like copper 64 will be an exception. I'm going to have to worry about that one. You know, bromine 76, it's on the order of hours. I don't have that long, so I've now got a fraction of it again. But if I'm doing rubidium 82 or something, you know, you're doing a 10-minute study, I've gone through, you know, a lot of half-lives at that point. So, so I just copied the top one from here, right? So that's just from the previous slide, just as a remember thing. So we're going to make an assumption that the half-life is very large proportional to our time, right? So if you think about the original equation, right, dn dt, I can change that to delta m delta t, because it's now getting down amongst the rate at which, you know, decays, you're talking 0 or 1 happen in a time period type of stuff. Very low rates to them. So we can kind of rewrite this equation here. Notice I threw out the minus sign. Why can I throw out the minus sign? What does the minus sign tell you? It's decaying, it's going away, right? In this particular case, I'm not trying to figure out whether it's going away or not. I'm actually going to treat this as is, right? That I'm just saying the number of decays that are happening, right? I just rewrite that equation, multiply through by dt, which is small, and I get this expression, right? Small number of decays in my time period, 0, 1, 2, something on that order, as opposed to if I was on the order of the half-life, where, you know, I'd be dealing with, you know, thousands upon thousands of these things, millions even, right? So I'm down to a very small fraction. This right here that results from it is actually the Poisson parameter. So it's going to turn out these decays are going to be Poisson distributed. And it's kind of neat that this turns out to be the parameter for Poisson. Now, if you remember, Poisson's parameter that's in there is both the mean and the variance. If you remember back to whenever your stats class was, right? So that means that you would expect that the decay rates in these small periods will move towards this value, right? So the delta n, you can kind of think this is in essence what you get when the delta n is 1. Right? This is going to turn out to be, in essence, this is not only the rate of what it is, but it's also in a sense the probability that you get one decay in that time period as that time period gets slow, right? As you move to tinier and tinier, right? In order for you to end up with this over larger delta t's, as delta t gets really small, this becomes probability that any particular one goes. Right? So that's kind of a neat thing. Probability that there's 0 is 1 minus that when delta t is really, really tiny. So you'll see that often listed. I think the book probably even lists that one. That the probability for 0 is 1 minus this. And this is the probability for 1, assuming delta t is so small that the likelihood of getting anything more than 1 is negligible. Therefore, the two of them have to add up to essentially 1 as the relationship that's in there. This is the actual expression for it, that given that there are n decays, which is equal to whatever the k is for the parameter, and a is this. Right? So what we will often do, right, we actually don't often calculate off this. You can typically do a calculation by just integrating this with respect to time. Okay? So if this is, in essence, the mean, how many of them are going to happen, or the probability if it's really, really tiny, if I were to integrate that over time, that should tell me how many I get, assuming the final integrated time period is still small compared to your half-life. So if I'm taking, you know, let's say in little chunks of seconds, but I'm still dealing with something half-life in days, and I'm doing a 10-minute image, then I can just integrate over that entire 10-minute time period, right? And if this is on the order of seconds, you know, 10 minutes is 600 seconds, so I can just integrate from 0 to 600 of this expression, you know, with delta t, right? The little delta, or your small t increments. Treating this now as my t, right? Those are those little small increment of time that I'm taking. So I end up with a t dt, and so I just get that 1 minus the equation, which is exactly what we expect. So you'll get those integrations. So I can just use this one directly for most of the small intervals, provided that your half-life is much bigger than your total imaging time. All right. As it gets closer and closer, then you have to use the entire lovely expression and deal with it from there, because you can get some changes if the net time is getting closer. All right. Well, like I said, many of them are not. So what we'll do is we'll actually kick up the dose that's in there, right? However many of them, the number of particles. Because the decay time is so slow, most of them you'll just excrete them out before they ever decay. The nice advantage of that is it gives us a little bit of a safety margin when applying them to you. If the half-life is much larger, right, it's not going to change that much if there's a 10-minute delay on getting you into the imaging area. If the decay rate is faster, then we're not going to want to actually give it to you, you know, until when you're basically in the facility, right, because the drop rate is going to be so heavy. Typically, if you're looking for a more static condition inside, you want these longer time rates and a higher number or concentration of them. A lot of them will just get wasted, but that's life. Do we feel good with this? All right. So that's where they calculate what do we need in order to get. You use the I for the detector to match, and then we calculate the number of decays from here. And that tells us, from this we can figure out our lambda, what lambda will be needed. So for instance, we might say, hey, I need a total, 7 million photon hits or something, right, to get a good image. We calculate what we want. And then we'll take that intensity equation plus this, and we can calculate what our I or what our lambda has to be to meet that I requirement. Given I want to do like a 10-minute time period or something. Right?
So are there reasons why you'd want a higher or lower intensity, like where you're imaging, or?
So you need a particular intensity to be able to image whatever's on there, right? So we know you need a certain intensity for the detectors to be able to pick them up and to be able to image them.
Okay.
If I'm doing a whole body scan, we can look at, imagine a virtual quality, right? The higher the intensity goes up, that's your signal, right? Versus the background noise that's in there. I need to achieve a certain signal to noise ratio. So that's why these are often very grainy, because we're trying to find the minimum signal to noise ratio to let the doctor see these are the areas. We could get the image better.
Right.
But if we got the image better, we're delivering more dose. If we deliver more dose to the patient, then the doctor has less dose they can use to treat. Imaging dose plus treatment dose has to be below a certain amount for tissue to survive. So the more we use for imaging, the less you can use for treating.
So is the amount of intensity to get you that scenario you want going to vary a whole lot?
Not hugely. There's some basic guidelines,
Okay.
that people use based on your particular system, how long you want the study, how big is the area you're looking in, what are you expecting the spread of this to be, type of stuff, right? And you have some basic guidelines, and then you give a little safety margin range in case it's spread further than you thought. And then you say, okay, I need at least this many, but I don't want to go beyond this number because that's going to, in essence, give too much radiation for no reason to the person. And then we use this equation basically to calculate the lambdas, and we'll find, okay, we want lambda to be between these values, and then we look up in the charts and see what is it. Okay. So that's the basic idea of what it is. Now, for a lot of these, this is a fairly standard procedure. So for a lot of them, it's going to be done once. It's going to be very similar for most people. We know we're doing this type of imaging. This is the one we want. Okay. All right. So let's see how do we actually calculate. This is the anger camber that I mentioned at the beginning. So this one in particular is a planar scintigraphy system. And remember, multiple of these from different angles gives you spect. So, and over the next couple slides, we'll kind of take a look. But basically, we're going to have a collimator that's going to be in here. We're going to have a crystal that's going to turn our high energy photons into low energy photons, but more of them to make it easier to detect. And then it's still going to be a weak signal, so we're going to have photomultiplier tubes in different areas, and depending on where it sees it, it's going to amplify it in that particular location. We'll talk about how they do that. That'll give me a strong signal. This then will have the tubes, will go into like a little digital logic circuit somebody's going to build that says this tube lit up, this was its physical location, and here's its time. So we basically build a logic circuit that will tell when it hit, how big it was, things of that sort. Did it hit a big enough spike that it was a main one as opposed to a scattered one, which will have a different profile. We'll talk about where that goes in. So that's the pulse height analyzer to figure out was it Compton scattered or was it the real thing. It will have a gating circuit which will say, yep, we indeed wanted that, and then it'll let the XY in, and it'll accumulate into the image to build up what's going on. That's the basic circuit. So on the right, you can actually see a couple different, the collimators could be a couple different things. The most basic is just straight in, right? But I could actually have them all kind of narrowed in and aimed towards an area. Imagine if you were trying to concentrate particularly on some small area within the body. By doing this, you're going to reduce some of the imaging problems that are going to go in, right? Because since they're kind of narrowed, aimed at that particular location, areas from different areas of the body won't actually interfere with it, and I'll get a very good direct shot. So like for instance, if I'm trying to measure perfusion within your heart, I don't want this being uptaken by other muscles in your body and having those ones blur my image. Right? I want to throw those other ones out because I care about your heart. So B makes a lot of sense if I'm doing a heart imaging situation because I know other big muscles are also going to uptake it. I just need to get rid of them. So, having them kind of aimed towards the heart makes sense. If I'm doing a general broad measurement across, your entire body, I'm going to want a wider range of these if I was, for instance, just looking for problems somewhere in your body. So now at this point, I'm willing to sacrifice some of the precision and sharpness of it to be able to get a wider detection range. This one's called a pinhole for obvious reasons. If I'm just getting one particular image, I just want that single shot coming in. It allows me to get a very precision to it. And you can get a weird focus out of a pinhole. Anybody ever see or know the fact that pinhole actually focuses?
Yes.
Did they cover this when you went through physics?
Yeah.
It's kind of one of those cool things that's on. If you've got glasses and never forget your glasses, this is kind of a fun thing. If you take your glasses off, those who have glasses, make a little tiny hole and you just kind of look through at a paper on there, you'll notice if you kind of squeeze it down to where it's about the size of a pinhole, you'll actually get a clear image. It'll be dimmer because less photons are coming through. But a hole actually focuses like a lens. This is how pinhole cameras work and stuff like that. You can actually take, really tiny, and then get a piece of text in front of you, and you can literally kind of focus in, and it will clear the text up. It works good for kind of that short range focusing. That's on there. You can do the same thing, take a piece of paper, stick a pin in it, hold it like a foot above something else and get your eye up. You'll see it actually magnifies, or sorry, not magnifies, but actually focuses. Because what it's doing is it's removing all the other blurring stuff. So I can actually use this as like a pinhole camera type setup. Anyway.
Actually, I have a quick question. So in X-rays, when we did collimating at the detector, a big purpose for that was to remove constant scattering.
Yeah.
But the book mentioned that for these kinds of, chapter 7 didn't go through the difference between spectrum and PET, but it mentioned that our decays are very monoenergetic, and so we can discriminate constant scattering based on energy at the receiver. So are these mainly just for physical locations of interest, like you were saying, or do they have a secondary?
No, they have a second. In essence, the Compton scattering is actually going to be handled by that pulse height analyzer.
Yep.
We'll talk. Right, so you'll see, usually you get a curve that looks like this, right? This is your Compton plateau, and that's the Compton drop-off. Here's your actual pulse, and we'll only let through things since we know the energy of this precisely, because of its source. We know the energy, right? As opposed to our X-ray sources, right? Remember that was spread across a range, so we don't know the exact energy of the source. We know the peak, but we don't know the exact value of the source. But we knew the direction there.
Right.
So direction let us screen it out. Here, I know the energy precisely, but if you're considering, here's your person and here's my detector right above it, I don't know where it's coming from, and I sure as heck don't know the angle it's at, right? So I don't know the direction, right? So this is not as good for that type of a directional removing. But what will happen to it when it's coming in, I don't want something, in essence, I get a focus off these. If you consider a series, and I should give a picture of this later on. If you consider for each one of these, there's a range of what can be included, right? So this is what's sometimes called a depth-dependent blur. The deeper in I go, the bigger, in essence, the relative pixel is that I'm dealing with, the image where you're actually resolving it. And that's really what it is. So it does have a spatial thing. It determines how big, in essence, it is the body. That's why we want this close, because the depth-dependent blur we don't want to go. But we want these to be fairly big because it'll keep this tight so it doesn't grow too bad.
Okay.
So it's really for trying to get a good clarity into the body for separating the mouth. That's kind of the main function. And in here, by focusing them all in one area, I'm getting good resolution right on the heart by removing any other possible thing. I'm not allowing any of those other things to come in. Just like when you're doing the pinhole, right? The reason why it focuses, it removes all the other light that's coming in and getting overlapped. And if your lens was doing what it's supposed to, and as somebody who's officially needs glasses, when I need to read stuff, mine does the same thing, it blurs it. So it's not aiming it to concentrate in the one area where it's supposed to. It's a little bit off. By removing those extra photons, I can effectively remove the thing that's causing the blur, therefore I get a clear image, as opposed to glasses, which just corrects the aberration so it hits right on the back of the lens. So it's doing it by a different means, but it still clarifies.
Okay, great.
Right, and that's by and large what we're doing here.
So the actual pinhole would be objectively better, except you'd need a much higher dose? Is that
Well, if I'm trying to actually resolve, like this one, I'm only getting one little beastie, right?
Right.
You know, that's in. Now, you know, when you're looking at, you know, this area, right, I can only get so much coming in, and that's what you're trying to pull off it, right? But if I'm trying to get a larger area to do, if you're doing a single pinhole, you can get, I could actually even have multiple scintillators and read it across here. I'll be able to resolve something. But the rate is slower. So if you've ever seen have you ever seen an old pinhole camera or used one before? They're really slow. So when they did it, like people would take the lens cap off and they'd let it sit there for a while, and then, you know, they time it, and then after a few minutes they cap it back on, right? Modern ones, to avoid the vibration, they'll still do this for long exposures, but you're literally, it's a much longer exposure time to get an image that's going on. But it does allow you to actually get, you can from this single thing get actually a fairly decent resolution. But since you're throwing so many photons out, it's just, it'll take so much longer than an original system did. Okay, quick things on how the rest of these work. So photomultiplier tube, right? Light photons comes in, there's a photocathode, the photon hits it, releases an electron, right? You know, maybe one, maybe two, whatever. There's a little bit of a focusing grid, so we put a charge across this and it basically pulls it through, and we'll aim it right at here with this curve one. And if you notice, there's this cascade, which means there's a voltage difference all the way down. So in essence, there'll be kind of an effect from here to here, right, where this is aimed at it. When it hits here, the single electron hitting here will get multiple electrons coming off because of the potential. And the difference between here and here is going to cause them to get pulled over here. Where it'll ram into this, you know, so maybe I have 2 come in, and then I have 4, and then I have 8, and that's, right? So it literally, as it bounces off each one of these, you kind of get an avalanche effect going on as they progressively hit. So it is an amplifier, right? An analog amplifier of them, and then they hit that anode, and you can see the capacitor that's on there, right? It'll filter it a little bit, and you've got a spike, and that spike is proportional to how many hit, which is proportional to how strong the photon hit here, right? the photon, if it had more energy here, it'll release more electrons to go through this whole sequence. So how many electrons make it to the bottom, since the amplification will be constant, right? The number of electrons that hit the bottom are proportional to how strong the photon was that came in. So you've got a good measure of what it is. So that's basically how a photomultiplier works. Good? Okay. All this is they arrange them, right? I want a circle, they've arranged a whole bunch of round ones in this. There are square photomultiplier tubes that are out there, and they put them in square arrays. There's a bunch of them. But this is just to say they'll put these in, and this is what the logic is trying to say. This one hit, and so I'm going to have to release the XY coordinates of it and how strong it was. That's probably a good spot to stop so we don't go overtime on them. We'll kind of finish up on these. But this gives you an idea of how they set up a basic anger camera. We'll finish the last couple components and I'll go from there. Yeah.
Would you be able to upload this PowerPoint?
Yeah. Yeah, so I was going to try to link it before I got here, and then when I made this PowerPoint, it stored it on the cloud, and I don't know why it automatically defaults to the cloud, which I despise. So I couldn't find it. But yes, I will link this for you before next time.